The University of KwaZulu-Natal's College of Agriculture, Engineering and Science is committed to making a difference in our world, from the classroom and laboratory to the field. It provides one of the finest study and research environments on the African continent and is recognized internationally as a center of excellence. Agriculture, Engineering and Science is one of 4 colleges that make up the University of KwaZulu-Natal and is home to over 8,700 students and approximately 700 staff. 3 of the university's 5 campuses form the core of agriculture, engineering and science activities in the region. The college comprises 5 schools: Agricultural, Earth and Environmental Sciences, Engineering, Chemistry and Physics, Life Sciences and Mathematics, Statistics and Computer Science. Engineering is offered on the Howard College campus, Agriculture on the Pietermaritzburg, and all the other sciences on both the Pietermaritzburg and Westville campuses. Exceptions are Agricultural Engineering, which is offered in Pietermaritzburg, and Geology, which is offered at Westville only. To compete with the best and to meet the challenges of the 21st century, South Africa needs highly skilled professionals in the areas of agriculture, engineering and science. We offer a wide array of interesting and innovative degree programs that open doors to a variety of different careers. Some degrees are unique to UKZN and are not offered at other tertiary institutions. For example, we are the only university in South Africa to offer a fully accredited agricultural engineering degree and one of only 2 universities in the country to offer a BSc in land surveying. Our postgraduate food security training program is the only one in the world, and we have the widest range of agricultural disciplines at any single South African or African campus. The choices of degree and the options on offer may seem confusing at first. Engineering degrees are more specific, and the options are usually career-focused. Emphasis is placed on training in the specific principles which engineers deal with in their professions. Engineering offers 7 different professional specializations. There are also degrees in land surveying or geomatics and property development. In science, there are structured or career-focused degrees. These include fields as varied as chemical technology, marine biology, industrial and applied biotechnology, and computer science and information technology, to mention a few. There are also more general degrees with a lot of flexibility. In this case, students have the choice of studying a BSc M stream in maths, physics, computer science, and statistics. All of these have a strong mathematical component. The other option is a BSc LES stream with a focus on the life and environmental sciences with subjects such as geography, genetics, botany, hydrology, zoology, ecology, and microbiology. In agriculture, there are various different options that involve practical and scientific applications. Students can combine science subjects with specific agricultural disciplines for a 4-year Bachelor of Science in Agriculture degree. These are more career-orientated. Agriculture and agricultural management are 3-year degrees with a higher practical component. Dietetics is a professional qualification that deals with the role nutrition plays in the promotion of health and the treatment of disease. Most degree programs across the college have field trips and projects that contribute significantly to the curriculum. This ensures that students learn in real-life situations under full field conditions. Many of our lecturers have received Excellence in Teaching awards, are recognized internationally, and are rich in practical experience. Students have access to excellent facilities that rank amongst the best in the world. 300 million rands has recently been invested in new teaching and research facilities, state-of-the-art laboratories, and improved equipment. The 30 million rands new School of Engineering building is the envy of engineering campuses across the country. Agricultural students have access to a 356-hectare research and training farm situated near the Pietermaritzburg campus. This facility provides students with hands-on training and is used extensively as an outdoor laboratory for teaching and research in areas such as animal and poultry science, horticultural science, and agricultural engineering. Adjoining Ukulinga is the Bisley Valley Nature Reserve, which supports a diversity of plant and bird species, as well as some large mammals. It provides a rich learning and research environment for staff and students. Based on the Westville campus, the college possesses unique facilities for research into higher voltage power transmission. These facilities are available in only 3 other places in the world and form part of the ESCOM-sponsored Science and Technology Innovation Park. The Science and Technology Education Center showcases the college's scientific achievements and promotes the public understanding of science, engineering, and technology within the region. The college houses a wide range of sophisticated equipment in its microscopy and microanalysis units, staffed by highly qualified and skilled technical specialists. The College of Agriculture, Engineering and Science prides itself on its graduates who are highly sought after. In a market characterized by a shortage of qualified professionals in science and technology, our graduates are readily employed around the world in the fields of agriculture, science, commerce, industry, engineering and research, to name just a few. Research plays a major role within the college and operates at the cutting edge of technology. College has the highest research output in the university and produces the most research publications. There are over 60 well-established research groups and centers within the college. The African Center for Crop Improvement caters for students from all over Africa. It is one of only 2 African plant breeding programs on the continent. Based in the School of Agricultural, Earth and Environmental Sciences, the African Center for Food Security focuses on alleviating hunger in Africa. It offers food security training programs, undertakes academic and applied research, and provides policy and program support. Promoting sustainable engineering practice is the Center for Research in Environmental, Coastal and Hydrological Engineering, or CRESH. It deals with the interaction between engineering and the natural environment. The Mechatronics and Robotics Research Group in the School of Engineering provides an excellent research and education environment for its senior undergraduate and postgraduate students. Judged one of the best research centers at the university, the Center for Plant Growth and Development focuses on high-quality research in the plant-based disciplines of plant physiology, plant molecular biology, and ethnobotany. The Center for Quantum Technology deals with physical phenomena at the microscopic level. Quantum physics led to the development of the transistor and the laser, and is currently being used to develop quantum computers and quantum cryptography. The college is committed to access and readdressing the disadvantages and inequities of the past. The highly successful Unite Engineering program and the Science Access Foundation and augmented programs offer alternative access to university, equipping students from disadvantaged backgrounds with the skills and knowledge to pursue their degrees of choice. Both these programs contribute significantly to advancing Black African scientists and engineers in South Africa. Staff and students contribute to a number of outreach and community initiatives that focus on social responsibility, sustainable development and upliftment of the wider community. The college also engages in activities involving the pursuit and understanding of science, engineering and technology through exhibitions, festivals and roadshows that target high school learners and the general public. The college has minimum entry requirements for its programs. These differ from degree to degree, but all require a national senior certificate and minimum performance levels in mathematics and either physical or life or agricultural sciences. For those who do not meet the minimum requirements, access programs are available. Additional information and brochures can be obtained from the contact information accompanying this video. The College of Agriculture, Engineering and Science is proud of its contribution to the university, the region and the country.
UKZN is one of the best. I definitely understand it's one of the best in South Africa. So for me, there was no other institute that I would have preferred other than UKZN.
We have the best facilities here in terms of laboratories, in terms of equipment, in terms of human resources, in terms of literature.
UKZN is one of the best universities in the country that teach agriculture or natural sciences.
What I think is good about this college is the level of international collaboration that we have. We have friendships with universities all over the world, which means that we're keeping up to a great international standard.
UKZN has got much more facilities and it's recommended worldwide to do your science studies here. Life begins here. Yes.
We continually strive to be academically excellent, innovative in research, and critically engaged with society. We invite you to join us or work with us to be part of this exciting team.
I'm only doing this for fun, okay? Yeah, sure you are. Are you ready for this? Please. How difficult can competition in South Carolina be? one chance, 2 minutes to bring on the students. I'm Cynthia. I'm going to be leading you guys into a combination team, and then we're going to
Yeah, they on. Yeah, every day. But they already on. Yesterday. Yes, it was.
Lesson didn't start. Didn't start yet. Yeah.
Okay, students, we apologize for the delay. We've got a little bit of a technical issue. The tutor will be on in about 2 to 5 minutes, right? Please bear with us. The section we'll be covering today is chemistry.
No, it only enters Zoom.
Hi, I'm on. Okay, good afternoon and welcome to this Matric Learn program. My name is Dr. Bissessur and I'm going to take you through some of the, can I please have a show of hands that you could hear me clearly? A thumbs up. Thank you. Okay. Right. So firstly, okay, Zanele, you got your hand raised. Oh, okay. You're saying that you can hear me clearly. Okay, great. Right. Firstly, let me just share some strategies on how you study, what you do, and what's the best way forward. I'm sure you've got quite a lot of information from other people how to study. But when it comes to chemistry, okay, when it comes to chemistry, the best or the most important aspect of chemistry is to understand the fundamental, okay? So I'm going to go through organic chemistry. So if you basically look at organic chemistry, you've got to understand the nomenclature. You've got to understand the basics. And then you've got to go through the reactions of organic chemistry. You've got to understand the structures and so forth. You cannot go to your exam paper and you cannot start answering those questions if you don't understand the basics. So for example, if you don't know the difference between an ester and an aldehyde or a ketone, so those functionalities, right? And in terms of basically, if you are carrying out reactions, right? What is a hydrolysis reaction? What is an oxidation? What is a reduction, etc., etc. So it's very important for you to understand the fundamentals. So what I would like you to do is that if you have your notes, is to have your notes with you together with your exam paper or with the past year exam papers or the question that you have. The second most important thing is to read the question and understand the question. You cannot see one word and simply start answering the question. You've got to know exactly what that question requires. Okay, so I'm going to start off with a bit of organic chemistry. I'm going to go through the fundamental, and then I'm going to give you a structure how to understand some of the questions that they're going to ask you. All right, so I'm going to spend the next 45 minutes going through some organic chemistry. So I want you to, I'm going to share my screen. Okay. Okay, just give me a few minutes and I'll just share my screen with you. Okay, can everybody see the screen? Can I just get a show of your hands or a thumbs up if you can see the screen? Thank you. All right, let's get going on. Right. Now, what's the important aspect of organic chemistry? Okay, right. So we're going to start off with what is organic chemistry, right? And I'm going to use this textbook because it's actually quite a nice textbook, but whichever textbook you have, it'll give you the same information as far as alkanes are concerned, right? So the chemistry of carbon. So when we talk about organic chemistry, you know, it's carbon, hydrogen, and oxygen. So the chemistry of organic chemistry is basically the chemistry of carbon compounds. And carbon has the ability to exist in a number of geometries and to bond. So, you know, you have, like, if you look at glucose, you look at ascorbic acid, you look at surfactants that we use in a lot of detergents. So organic chemistry finds its hands in quite a lot of applications, right? So I'm not going to go through the hybridization states, okay? Mr. Govender, could you please, yeah, thank you. So there are three types of hybridization states and geometries found in organic chemistry. I'm not going to go through that. That's just telling you about the geometries of the carbon compounds. I'll try and go through, explain to that or what that means. But generally hydrocarbons, okay? So there are four basic types of hydrocarbons. We have alkanes, alkenes, alkynes, and aromatic hydrocarbons, right? So now when we look at alkanes, okay, alkanes contain only single bonds. These are saturated hydrocarbons, and they are called aliphatic alkanes. So they can be straight chained, branched, or cyclic. And you know they have a general formula CnH2n+2. I'm sure you know this, but I'm just refreshing your memories, right? So when you look at an alkane, or if you're looking at a hydrocarbon, you can see it's a saturated compound. That means the carbon has 4 bonds. All of these compounds have 4 bonds. So you know in organic chemistry, we like to have a structural formula. So you can see the structure of methane. You know methane is a gas, right? We have methane, ethane, and you can see we refer to this as a homologous series. And then we call this the molecular formula or the condensed structural formula. So you will see this you generally don't see the ball and stick structures. I'm sure you have seen it, or the space filling orbitals. So let's not worry too much about that at this point. So let me move on. Right, so here you can see the molecular formulas, right? And you can see the carbon numbers are increasing, carbon 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And you know the homologous series, which we start off from methane, ethane, propane, butane. So these are gases. Then we come to pentane, hexane, heptane, octane. These are liquids. So you can see the boiling points are starting to increase. And then we go to nonane and decane. And you know octane is one of those very, very, very important aspects that we have, which is petrol, right? Only van der Waals forces, which basically are London forces that exist between these molecules. And you can see boiling point increases with chain length, right? So I'm just giving you a trend, which you basically can understand. All right. Now, the structures of alkanes, I'm not too worried too much about we say that the carbons are sp3 hybridized, and the tetrahedral geometry, don't worry too much about that. Let's move on, okay? I'm also going to miss all of these, and I'm going to go to isomers, right? So you know in organic chemistry, you have isomers, which means they have the same molecular formulas, but atoms are bonded in a different bond order. So you can see all of these here, right? So you can see butane. You've got 1, 2, 3, 4. And in this structure here, you've got 1, 2, 3, 4. And in this structure, you've got 3 different isomers of butane. So you find that the order in which these atoms are arranged are in a different order, right? Now, you can see also in pentane. So the straight chain, which is 1, 2, 3, 4, 5 carbons, you can see with the isomers, as soon as they start to branch to methyl butane, what has happened? The melting point and the boiling point changes. So you can see this had a boiling point of 36 degrees in pentane, but when we go to 2-methyl butane, it's also a 6-carbon member. It's an isomer of pentane, but you can see the boiling point has decreased because of the branching. And then we go even lower. So you can see 2,2 dimethyl propane, you've got a boiling point of 9 degrees Celsius. You'll notice I'm using the term pentane, 2-methyl butane, and 2,2 dimethyl propane. So you know how to look at the nomenclature, right? So you can see in 2-methyl butane, you've got the longest chain, 1, 2, 3, 4, which is, so you start with methyl, ethyl, propane, and butane. That's the parent compound. And you can see you have a methyl group on the second carbon. So we started to number from the left-hand side or you can number from the right hand side, it doesn't matter. So you can see the nomenclatures are quite important, right? I'm not going to go through conformers, right? You haven't done all of these here. So I want to go through the nomenclature because this is very, very important. And in your exams, they're going to ask you to name some of the organic nomenclature. So you have a parent, it tells you how many carbons are in the longest chain, right? So organic nomenclature means naming organic compounds. So there are three parts to a compound name. So we call it, the first one is the parent compound, and it tells us how many carbons are in the longest continuous chain. And the suffix tells us what type of compound it is, right? And then we have a prefix, tells us what groups are attached to it. So these are the three things, and you will see now what we mean. Right, to name a compound, we find the longest chain in the molecule. We number the chain from the end nearest to the first substituent. We list the substituents as a prefix along with the numbers of the carbon. I'm going to show you an example, so don't be too perturbed. And if there is more than one substituent in the molecule, list them alphabetically. So methyl, ethyl, propyl. Right. Now, you also have cycloalkanes, and these are basically cyclo compounds if you come across this, but I don't think you'll come across too much of these cyclo compounds, right? Or cycloalkanes as we call them, right? Even cyclo substituents on cycloalkanes, I'm not going to go through that, okay? Right, reactions of alkanes. Now, because of its structural role, alkanes are relatively unreactive, right? So alkanes are relatively unreactive compounds, and forcing conditions are required for a reaction. Combustion, that means we heat alkanes. We've got to heat them. And obviously we have what we call free radical reactions, right? And in order to predict the product of a reaction, it is important to be able to distinguish between carbon types in an alkane, which means you may have a primary, secondary, tertiary, and quaternary carbon atoms, right? So let me just take you through this to show you reactions of alkanes, right? So you can see there we have an alkane, and you can see all the different substituents, etc., etc. Right. Now, reactions of alkanes. Don't be too worried, because what I'm just trying to give you an overview of organic chemistry, and then I'll come back to some of the naming, and I'll go through the naming of the compounds, right? So you can see there's a whole, I've got this reactions of alkanes, right? And you can see, where is the alkane? Here is the alkane, right? And can you see, you've got a CH2CH3, you can put a substituent and you can get an RX, right? If you add ammonia, you form an amine. So I'm sure you've seen basically how you can go from an alkene to an alkane, right? So this shows how the reactions are linked. Now, what you are seeing on this slide is all the different types of substances. So you got a ketone, an aldehyde, a carboxylic acid, but here's the alkane. And you can see, if you put on a substituent, you can form an alkyl halide. So the X is basically a halogen, which you can put onto the alkane, right? And you can see it's very difficult to go from an alkane directly to an alkene. So we've got to go through an alkyl halide. So when you put on a halogen onto the alkane, then you can go to the alkene. If you add water to the alkene, you will make an alcohol. And then if you have oxidation of the alcohol, you form a ketone, right? I'll show you some specific reactions just now. Now, we also talk about combustion reactions, right? And you know, if you take any organic compound and if you heat it, you will only form carbon dioxide and water. So the complete combustion of any alkane only yields carbon dioxide and water, all right? Then we talk about free radical reactions, and you can see alkanes react don't react in the dark. So in reaction 1, if you took methane, for example, and if you have chlorine, okay, chlorine gas, there'll be no reaction in the dark. But as soon as you put them in the light, you can see it forms an alkyl halide. So this type of reaction is called a substitution reaction. Okay, so if I take you to the previous slide, you can see we got the alkane, and you see when we're talking about the substitution, it means you can basically form a substitution reaction. And here's an example in reaction 2. So alkanes are not reactive in the dark. So you've got to basically have light for an alkane to react. And you can see when you have methane with chlorine, in this case, it may be chlorine gas reacting with methane gas. And if you have light, you will generate CH3Cl plus CH2Cl2 plus CHCl3, and you can form any one of these compounds. Okay, so you can control this reaction to target which reaction you want. So the free radical halogenation is also an example of a radical chain reaction, right? Now, such reactions are characterized by 3 steps. We have an initiation, a propagation, and a termination reaction. So initiation produces the first free radicals by a homolytic bond cleavage. Simply what we're saying is you've got to initiate a free radical reaction. And if I take the chlorine, and you see when I subject it to light, I've actually broken this bond and I formed a radical, and radicals are very, very reactive. So I've got this radical that's reactive. Now, the next is the propagation, and you can see it involves a series of reactions which generate other radicals. So simply in the previous slide, I got chlorine. Remember I said that, remember I said that for alkanes to react, if you have in the dark, there'll be no reactions, but if you have light, you will cause it to react. Now, in this particular reactions, I'm showing you a substitution. That means you're putting on a halide onto a methyl group. In this case, it's alkane, right? So here it's methane. And now can you see you substituted 1 chloro onto a CH4. Then you can put 2, then you can put 3, and then you can completely substitute all the hydrogens on methane for chlorine atoms. And obviously, the longer you're going to leave it in light, the more chlorines you're going to substitute onto this carbon. And this is called a substitution reaction, right? So then we talk about free radical reactions, and I'm showing you the mechanism of the free radical. So this is the initiation. You break the bond for the chlorine and you form a radical. Can you see you have 1 electron? So when you broke this bond, 1 electron is going with each chlorine atom. So you've got 2 chlorine radicals that's formed. So the initiation produces the free radicals that we have. Okay, then you can see we have the propagation, meaning the radical is very reactive now, and it starts to react with the I'm only using methane as an example. You can have other alkanes as an example. So can you see what this chlorine radical has done? It's reacted with one of the hydrogens. And can you see what's happening? The reaction now will continue. And can you see we've now generated a CH3Cl. So you see how this reaction has taken place. So first you initiated the reaction, you've got HCl, then there's a radical now with the methane group, and that now takes on the other Cl. So you see what has happened. It takes on another, so this radical becomes, this radical becomes reactive, and it reacts with this chlorine radical and it forms a CH. So that's how we get the substitution. Okay. Now, free radical reactions, you can see also we can have, you can brominate one of these alkanes. So this is what we call a cyclic alkane. It's a cyclic group, right? It's a saturated alkane. And again, you saw light, you saw bromine, and we can add the bromine. So I'm showing you some of the reactions that we have. All right. So I'm going to now just stop sharing, and I'm going to share another screen with you. So if you just hang on, I will share another screen with you. Okay, right. Now I'm going to go through some information in terms of organic chemistry, right? So let me go all of that. Right, let me start here, right? So now I said in the previous slide, so you have what we refer to as an empirical formula, right? Now, for example, let's look at N-butane as an organic compound. So you have an empirical formula. That means it's the simplest whole number ratio of butane, you know, it's C4H10. So this is the empirical formula. Then we show the structural formula. You can show the Lewis structure, you can show the 2D structure, the 3D structure, the sawhorse, and the Newman projection, right? Now, let me take you through this here. So you can see we have alkanes, right? And the name ending is ane. So for example, this is called ethane. It's got 2 carbons. Then you have an alkene. So you can see here we have ethene, okay? Then we have an alkyne, which has got a triple bond, okay? And then we have a halide. So if it's now here we got a carbon attached to a halogen. So you can see here chloromethane. And just now I showed you how we make chloromethane using a free radical mechanism, right? Then we have CH3. So you have a CH3 attached to an OH. So it's an alcohol. And this is methanol. So you can see CH3OH. Then we have an ether. So this is dimethyl ether, CH3O. So you can see a carbon attached to an oxygen attached to another carbon. Then we have an aldehyde. So it's a carbon double bond oxygen to a hydrogen. So this is an example of ethanol, okay? Then you have a ketone. So here you have propanone, okay? And this is the common name for this is acetone, which is nail polish remover. And then we have a carboxylic acid. So you can see organic chemistry starts with an alkane. That means carbon single bond carbons. Then we go to an alkene, which is a carbon double bond, and alkyne. Then you've got the carbon attached to an alkyl, a halide, which we call alkyl halides. Then we have the carbon attached to a hydroxy group or an OL. So you form an alcohol, we call it methanol. Then you have ether, okay? So you have a ROR, so you can see we have an ether, and then we have an aldehyde. So you should know these different functionalities, okay? You have esters, right? Methyl ethanoate, you have an amide, okay? You have an amine, and you have nitriles. But you should only concentrate on the ones that you've done, right? Now, let me take you through to the Iupac rules for naming compounds, right? I did say this before from the textbook. The parent hydrocarbon is the longest continuous and the highest priority. The chain is numbered in the direction that gives the highest priority functional group. If there is a functional group and substituent, the functional group gets the lowest possible number. If the same number for the functional group is obtained in both directions, the chain is numbered in the direction that gives the substituent the lowest possible number. If there is more than one substituent, the substituent are cited in alphabetical order. Now, I'm sure I'm reading this and you must be saying, oh, this guy is so boring, but just hang on. I'm going to show you the example now, right? I'm going to show you the example. So I'm going to take you through that rule of how to name a compound. Now, you should know this we refer to this as methane, ethane. So meth is 1, eth is 2, prop is 3, but is 4, pent is 5, hex is 6, hept is 7, oct is 8, non is 9, dec is 10, undec is 11, and dodec is 12. Hence, we have this naming of these compounds. So you know methane is a gas, ethane, propane, butane, etc. Okay, so now a couple of important points. All the names end in ane, which means that they're alkanes, right? So the formula for alkanes is CnH2n. What that means, if I've got basically 2 carbons, then it's going to be CnH2n plus 2. So that'll be, if I've got 2 carbons, then it'll be 2 times 2 is 4 plus 2 is 6. The hydrogen becomes H6. Okay. Right. Let's look at naming the prefix and substituents. So when you have side chains, they end with -il, right? So you can see, and if there are more than one particular substance, so here you can see we have 2, so this becomes dimethyl, right? So I'm just going to show you this, the branches: methyl, ethyl, propyl, butyl, and pentyl. So these are what we call, so when I said to you here, side chains having end in the word -il. So that means if you add something, so for example, in this particular example at the top here, right, you can see you got a substituent. I've highlighted it now. That is a methyl. If I had CH2, CH3, that would have been an ethyl. Okay, so you see, if you got an ethyl group, then you can put a propyl group, then you can put a butyl group, then you can put a pentyl group. Okay, now you also have special groups, isopropyl. Don't worry about these. I don't think you would have done these. Right, now let's look at this example and pay attention. I'll go through the alkanes, I'll go through the alkenes, and I'll go through some of the reactions, right? So if you look at the parent hydrocarbon is the longest continuous chain and contains the highest priority functional group. So let's look at this particular compound here. You got 1 carbon, 2 carbon, 3 carbons, 4 carbons, right? And you've got an OH group and you've got a carboxylic acid group, right? So in this table, we're saying that the highest priority, so here we got a carboxylic acid and we got an alcohol. So the alcohol, now this chain here will be known as a carboxylic acid, right? So here we're going to number it from the carbon closest to the carboxylic acid group. So you got 1, 2, 3, 4, right? So it's a 4, okay? It's a 4 hydroxy. In this case, it's 1, 2, 3, 4, 5 pentanoic acid, okay? So you can see it's basically a 4 hydroxy pentanoic acid. So I'm showing you here we have 2 functional groups, and the longest chain here is basically a 4 carbon. The parent compound has 5 carbons in it, 1, 2, 3, 4, 5. So you include the carbon in this group, right? So 1, 2, 3, 4, 5 pentanoic. So it's a 4 hydroxy. I'm labeling from the right hand side. 1, 2, 3, 4, right? Sorry, I must relabel. So it'll be 1, 2, 3, 4, 5 hydroxy pentanoic acid. Okay. I'm going to do an example just now, so don't stress about that. So you also have alkyl substituents, right? And so I showed you, you basically have aldehydes. Can you see you have aldehydes and you have carboxylic acids, right? So you can see in this particular example, you have a compound called butanoic acid. So remember, you start to number from the carbon that has the carboxylic acid. I'm going to go up now and show you the previous example that I spoke about. So in this example, you're going to label the first carbon as 1 on the carbonyl group. So the C double bond O, this carbon will be the first carbon. Then you've got the second carbon, third carbon, fourth carbon, fifth carbon. Therefore, I call it a 5 hydroxy pentanoic acid. Okay, so now let's look at the rules, right? Rule 2, the chain numbered in the direction that gives the highest priority in terms of the functional group, which gets the lowest possible number. So what we're saying here, can you see in this example here, the carboxylic acid will, the carbon that contains the carboxylic acid, so you start naming it from that point. So that's carbon gets number 1, right? Can you see for this aldehyde, you start naming the chain from where the aldehyde is. Okay. And rule 3 says, if the same number of functional groups is obtained in both directions, the chain is numbered in the direction that gives the substituent the lowest number. So in this example here, I'm going to now look at this. You got 1, 2, 3, 4, 5. You got 5 carbons. So I'm going to look at the first carbon as number 1 from the right hand side, because the first substituent is closest to this carbon. So you can see on the second carbon, I've got 2 chloro groups, right? And then the hydroxy group is sitting on the third carbon. So this is going to be 1, 2, 3, 4, 5 carbons, right? So the parent is a pentane. Can you see? Pentane. So the parent is a pentane. But close to it, I've got a 1.1. So on the second carbon, therefore, it's a 2.2 dichloro. Can you see? There's 1 chloro and there's another chloro. So it's a 2.2 because it's carbon 2 dichloro pentanol, pentan 3-ol, because this compound is an alcohol. So it takes on an alcohol functionality. So we don't start labeling the carbon from the left-hand side as 1, 2, 3, 4. So you don't get a 4.4 dichloropentane 3-ol, right? You get a 2,2 dichloro pentane 3-ol. We're saying 3-ol because we're showing that the alcohol is sitting on carbon on the third carbon. Okay, so let's look at this exercise in naming this particular compound, right? So you're going to get nomenclatures where you're going to name these compounds, and you can score marks from here. So let's look at this example. And you can see this is quite a horrendous structure. But what you're going to do is you're going to look at each one and you're going to count 1, 2, 3, 4, 5. So start with every carbon and look for the longest chain. So you can see the longest chain is 10 carbons long, right? So I've actually labeled it for you, right? 1. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? 1. Okay, 2, okay, 3, 4, 5, 6, okay, 7, 8, 9, 10. So you can see the parent compound is a decane, right? And what we're going to do is we look at that long chain, right? And so you will look for the longest chain, right? And then you will add your substituents as you go along. Right, naming of cycloalkanes. I'm not too sure if you've done cycloalkanes, but you will name the cycloalkanes with also the same rule where you have substituents closest to them. Okay, I'm just going to skip all of this and I'm going to show you this cycloalkane here. So in this example, you can see you have a cycloalkane and you've got a methoxy group, you got 2 halogens, and you got an alcohol. So this is going to start, you're going to start labeling from the carbon that sits closest to the alcohol group, because this carbon, this cyclo group is going to, the priority is going to be an alcohol. So that's why we say it's 1, 2. So you're going to go 1, 2, 3, 4. The dichloro, right? So it's going to be 1, 2, 3, 4. So it's 4,4 dichloro and a 3-methoxycyclohexanol. sorry, I'm gonna start again. If you go anti-clockwise from the hydroxy group, your methoxy group is on 1, 2, carbon 3, and the 2 chloros are on carbon 4. If I go clockwise, then I'm going to get 1, 2, 3 dichloro. Okay, so it's going to be 3,3 dichloro and a 4 methoxy, but because the functional group takes a precedent on that. Okay, I spoke about isomers, so you know what's isomers. You can see N-butane, and the isomer is isobutane. There's just a branch in between. Okay, there's a branch in between. Are you not able to see this document? Can everybody see this document? If you could just give me a thumbs up, you're seeing that you're seeing this document. Thank you. All right, cool. All right. Right. So let's look at now some okay, I'm just going to share another slide with you to go through the alkenes, okay? If you just give me a minute. I think I'll just share with my other. I think this is better. Okay, I'm just trying to find those reactions to give you. Just bear with me. I won't be long. I'm just finding those notes so I can just share with you. Okay. Sorry for the. There we go. Right, I found those notes on alkenes. And there's the alkenes. Okay, right. Let's look at alkenes. All right. So alkanes, you know alkanes, you should know the naming of the alkanes, you should know the reactions. Now let's look at alkenes, right? So I think mainly you'll cover alkanes and alkenes. With alkanes, I showed you the free radical mechanism, right? Now with alkenes, you're going to look, we obviously have a carbon-carbon double bond, right? As far as the alkenes. And then you have the alkynes, which is basically a triple bond. So for alkenes, you know it's CnH2n, because with alkenes, the bonds were saturated. So we took away basically two hydrogens and we formed a double bond. So it becomes reactive, right? So let's look, benzene is a cyclic alkene. You can see it's got 3 double bonds. And you know benzene is basically a solvent that we use quite a bit. Now we have alkenes, and you can see on this alkene, if you have two substituents, if you have both substituents on the same side of the double bond, we have what we refer to as a cis-2-butene. So if I look at the nomenclature here, you've got 1, 2, 3, 4 carbons. And in terms of the isomers, okay, you can have a trans and you can have a cis. So you can see in one case, right, the methyl group both are on the same side and we refer to it as a cis. And if they're on opposite sides, we refer to it as trans because they across each other. And you can see these double bonds exist, and we have 2 different types of compounds. And what do you notice? The melting points and the boiling points are totally different based on the cis and trans isomers that we have. Okay. So if you look at alkynes, right? So alkynes are basically triple bonds, right? Now, nomenclature of alkenes, right? So let's look at the nomenclature of alkenes. When you are labeling, again, you're going to see a double bond. With alkanes, you're not going to see a double bond. So we're going to choose the longest chain, the parent compound. So you can see in this particular example, I've got 1, 2, 3, 4, 5, 6, which is the longest chain. So it will be hex. If there was no double bond here, we'll call it hexane. Okay. If we basically have a double bond, the parent name at the end becomes ene, hexene. Okay. So you can see in this case, now the double bond is on carbon 1. So you show the carbon 1. And then if we going in terms of the numbering, we're going from right to left. So you can see on carbon 4, we have a methyl substituent. So remember, you're going to call this a 4-methyl 1-hexene, meaning the methyl is on the 4 position. Hex because you've got hexane coming from 6 carbons, and ene because there's a double bond on carbon 1. So we say 4-methyl because the substituent, the methyl group, so we have methane, but when it's a substituent, we call it methyl. And 1 because it's on carbon 1, right? So if you look at the next example, it's a branched structure. So here we're looking for the longest structure. But remember, you have to have your alkene with the lowest number, right? So you can see I didn't start from the methyl group that's sitting below the 1. So this is labeled 1, 2, 3, 4, 5, 6. I could have got a 6-carbon parent compound, but because we've got to start with the numbering from the lowest, the alkene must take the lowest number. And here you can see we numbered the chain 1, 2, 3, 4, right? Because we numbered the parent chain to give the first carbon of the double bond the lower number. So the double bond must take on the lowest number. And that's why we labeled it from this point. So if you got 2, and if you look below there, we've got an ethyl group. So coming from the word ethane. So it's an ethyl group. So on position 2, you've got an ethyl group. And on position 3, you've got a methyl group. So it's a 2-ethyl 3-methyl, 1-pentene. So 1, 2, 3, 4, 5. Pent is a 5-carbon parent compound. So you've got a pentene compound. So you see how alkenes are basically named. So the nomenclature for alkenes. If you come across cycloalkanes, these are cyclic groups that have an alkene on it. And you can see here again, you're going to start, right, with the one nearest to the double bond. So the one position, you can see where your carbon starts with number 1, 2, 3. So you got a 3-methyl cyclopentene. So here we don't say 1 cyclopentene because it's understood that the cyclic group will take on the lowest number at the first point of the double bond, right? Even in the next one, you've got the number 1 at the you've got basically the at position 1, so where you've got the double bond. Okay, so that's the naming, right? So we have some common substituents, and you can see when you have a vinyl group or an allyl group, you may have come across this. If you haven't come across this, don't be too perturbed as far as the common names and as far as these particular alkyl groups are concerned, right? I think I'm not too sure, but I want to make an appeal. Those of you that are on this group, if you want to put information on the group, please do it with an intention of studying and not, things that are not of the science study. So I will mute you. I will ask you to be removed if you are writing stuff that doesn't pertain to chemistry. Okay, so please refrain from writing unnecessary information. If you don't want to be part of this group, please leave the group. Okay, that's fine. You're welcome. All right, so some alkenes, right? There's some common alkenes that you find that you can come across. So we have ethene. Now ethene is a gas, and let me tell you about ethene. Ethylene, they actually spray this on fruit to ripen fruit much quicker and for it to enlarge. All right, so propene, you can see 1, 2, 3. So we label from the right hand side, and here we can say, instead of saying one propene, we just say propene because we know that the alkene is sitting on the first carbon. You also have common names for these alkenes, right? Ethylene, propylene, isobutylene, right? So these are very specialized names, right? And I'm not too sure if you've done alkynes, but here you can see, again, just like we did with the alkenes, you basically have the numbering of the guy that's putting all of these things. I'm going to, you can be charged because we know who you are, right? And you better stop that because we know who are interfering with the screens. I know who you are. And I'm going to ask you, we will actually take legal action against you. Sorry to the others that are logged on. So you can see for alkynes, you label as well like we did with the alkenes, right? So you basically will label from the carbon that's got the triple bond. So you can see we have a 3-methyl 1-butyne in terms of your labeling. Okay, so we have those. All right, so I'm going to go through some of these. Right. Now, physical properties, alkenes are non-polar. Okay, alkenes are non-polar. The only attractive forces between their molecules are dispersion forces, and their physical property, the physical properties of alkenes are similar to those of alkanes, right? Right. Now pay attention to this particular information. I'm going to talk about the reactions of alkenes, right? Please pay attention, because you can be given a question on the reactions of alkenes. Now remember, for alkanes, the only reaction that takes place, you've got to heat the alkanes at high temperatures for them to react, or we carry out free radical reactions where you have, I showed you that free radical reaction before this. So here we have what we call a hydrochlorination reaction. So if you've got an alkene, and if you reacted with an acid like HCl, can you see what you've done? You've simply put the H on one carbon and you've put the chlorine on the other carbon. Okay, so you basically now what you've done is you've chlorinated this alkene. So we call it hydrochlorination. That means you've added the HCl across the double bond, right? And this is carried out with pure reagents or in a polar solvent such as acetic acid, right? Now, the reaction is what we call regioselective. A regioselective reaction means that the chlorine will not just go to any carbon. So let me show you this reaction. If you've got propene, right? If you've got propene, so now does the H go to the first carbon on the double bond or carbon 2 on the double bond? Can you see where the chlorine is gone? The chlorine atom is gone on the second carbon. So if you react propene or the alkene with HCl, it doesn't just go anywhere. So we say this reaction is regioselective. Okay, and you can see the chlorine went onto the second carbon. Okay, and I'm not too sure if you've done Markovnikov's rule. That says the addition of HX or water, so an alkyl halide or water to an alkene, the H adds to the carbon of the double bond that has the greater number of hydrogens bonded to it. So here you can see the first carbon has 2 hydrogens. The second carbon has 1 hydrogen. So in the reaction of alkenes with HCl, right, which is hydrochlorination reaction, we call it the Markovnikov's rule. Okay. So here your H will go to the carbon that's got a greater number of hydrogens, and the chlorine goes to the second carbon. So we don't get 1 chloropropane, you form 2 chloropropane. So in your notes, your teacher may have gone through reactions like these. You've got to learn these reactions of the alkenes. Okay. Now, if you did, for example, 2-butene, let me show you this reaction. And if you didn't do a mechanism, right, a 2-step mechanism of 2-butene, in other words, we're showing you how this reaction took place, right? So in the first reaction, this electron pair now basically takes the electron pair bonds to this hydrogen here. And can you see what has happened? The first carbon, right, will now form a carbocation. And then in the second step, right, the chlorine adds to that carbocation to get the chlorination reaction going. If you didn't do reaction mechanisms, don't worry about it. But here we say it's a 2-step. So when you are carrying out a reaction or hydrochlorination on an alkene, the lone pair of electrons from the alkene is going to attach to the hydrogen, okay? And then you're going to form a carbocation, right? So you can see it formed a carbocation, and then you've got this chloride anion, and the chloride anion in the second stage, we say attacks this. So because it's minus, it goes looking for the plus, and you can see we formed a chlorinated alkane, right? So we formed a chlorinated alkane. So in this case, we form what we call a secondary carbocation. Okay. So if you did carbocations, you can see that it forms in the reaction mechanism. Right. Now let's look at this reaction or the addition of water to an alkene. So like we did, right, like we did with the alkene and we did with HCl, this is called a hydration reaction. And we can add acid. So basically, if we use sulfuric acid, we catalyze this reaction, right? So what simply happens when you add water to an alkene? You simply add the H and the OH, because water is made up of OH and H+. So you can see you add an OH and you add an H+ across the double bond, right? So the addition of water is called hydration. You know, when you hydrate something, you're adding water to something. And this reaction is also regioselective, but we say it's acid catalyzed. That means if we add sulfuric acid, we're going to form this reaction here. And again, you can see, according to Markovnikov's rule, what happened to the hydrogen from the water? It went to the CH2 and the OH went to the middle carbon. So we formed 2-propanol. So like you formed like you in the previous example, you formed, right? In this example here, I'm just going up. So like in the previous example, right? With the, I'm gone too far up, sorry. I'm just going to scroll down, right? So like in the addition of HX, right? You form the 2-chloropropane. When you carried out the reaction or the hydration reaction, okay, this hydration reaction, it was also regiospecific and you form 2-propanol, okay? Remember, we're adding acid as a catalyst. So if you're studying your reactions, I want you to learn it like this, okay? So if in your exams you get a reagent, you have to know where this reagent goes to, okay? So you have to know what happens as far as the reagent. Right. Now, again, we have a mechanism, right? We have a mechanism. Can I please ask the participants to mute your mics? So if we look at propene, now you can see there's the acid. There's the acid. That means, you remember when we said we're adding H2SO4, the H+ from the acid forms H3O+ with the water. And that's how we got this H3O+. So one of the hydrogens came from the acid. Then it makes now this lone pair from the alkene attacks the H+. And can you see now you formed an OH? So there you form the carbocation, and the lone pair now goes to attach to the carbocation. So it's a secondary carbocation because you got 2 carbons attached to the carbocation. And then can you see what happens, right? The OH attacks there and you form the H2O, sorry, attacks there and you've got an oxonium ion, right? Then what happens? You got your water that comes and pulls off a proton, and now you formed this particular compound. Okay, so these are the mechanisms. As I said, if you've been asked for the mechanisms, this is how you should be writing out your mechanisms in terms of the hydration reactions. Then we have another interesting reaction of the alkenes. We have a bromine goes across the double bond. Now this is easy, right? Because all you have to do is that both the bromines and you form a 2,4 dibromobutane. And here we add a solvent. It takes place in an organic solvent called carbon tetrachloride. Remember, we always said it's carried out with pure reagents in an inert solvent. So here we can simply take bromine and we can add it across the double bond. So whenever you see, if you took Cl2, you'll just add the Cl2. So we would have had a 2,3 dichlorobutane. Okay, so you can see bromination or halogenation. So if you took chlorine or bromine, you can add it across the double bond. Okay, so you learn your reactions. And here we show the mechanism. If you don't know the mechanism, don't worry about it. And I don't think you would have done the mechanisms of that. So now remember, we also can carry out oxidation and reduction reactions of organic compounds, of alkenes. Remember, oxidation is the loss of electrons, reduction is the gain of electrons. So you recognize using balanced half reactions, you write a half reaction showing one reactant and its product, and you complete your material balance, right? So now you use water and H plus in acidic medium, and you complete the charge balance. But in organic reactions, we carry out what we call oxidations with special oxidizing agents. So now, can you see what we've done here? We use osmium tetroxide, and you would have learned about specific reagents which oxidizes alkenes. And when you oxidize this alkene, you form OH across the double bond. So can you see here, we've got a cyclopentene or a cycloalkene, and you added OSO4. Now peroxide here is the solvent, right? So oxidations take place in solvents. So here we have a glycol, and here we have a cis-cyclopentane diol. So we're adding OH groups across the double bonds, and we do that by oxidation. So whenever you hear of the word oxidation of organic compounds, and especially alkenes and alkynes, you know you're going to put an OH group onto it. Okay, so go through your reactions in terms of your what each reagent does, and that's why I'm pointing this out to you. Okay, then opposite of oxidation is reduction. So pay attention to this, and I'm sure you must have done this. When you take hydrogen, can you see what you've done? You've simply added two H pluses across the double bond. And this is simply what we call a reduction. So in organic chemistry, all you've got to remember, when you're doing oxidation, you're putting oxygens onto your carbons. So an oxidation will add on an OH. So you put an oxygen, remember that. And for reduction, remember you're putting hydrogens on, right? So see what has happened here to the cyclohexene, right? You've got the double bond. And see what has happened when that means the double bond is now gone. And you simply now remove the double bond, you put two hydrogens on. So you see, you went from a cyclohexene to a cyclohexane. So you formed an alkane from an alkene, okay? So whenever you use the H2 and you got these catalysts, you're going from an alkene to an alkane, right? And that's done by reduction. So reduction of alkenes to alkanes, okay? Now you can also polymerize your alkenes, and you can see what has happened here. You've basically now, you will have an initiation reaction. So these occur by the free radicals like I showed you. So you initiate this reaction. Now the double bond becomes saturated and you start to polymerize. You'll have another single bond C, and you will start to polymerize this reaction. Okay, so go through these reactions in your textbook and what your teacher has given you. All right, I'm going to show you a few reactions. So for example, you can see H2O and H plus is a hydration reaction. Now BH3, H2O2, this is a specific reaction. We call it oxidation by borane, right? Now you must identify specific reagents that will do specific things, right? So you see, if we took 2-methyl-propene, you got an alkene reacting with HCl. So now you know what happens. The H plus and the Cl goes across the double bond, and the Cl will go to the carbon and the H will go to the carbon with the most number of hydrogens, which is Markovnikov's rule. So as soon as you see the two chlorines, you know the chlorines are going to add across the double bond. Then with H2 and platinum, you know it's going to be a reduction. With KMnO4 in water, it's an oxidation. You're going to have two OH groups across the double bond. And then O3 and Zn and H plus is also an oxidation using ozone. So you may not have seen these reagents, but in your textbook or in your notes, your teacher would have given you specific reagents to use on alkenes. So learn these reactions of alkenes, okay? And look at the reactions that you have, okay? So I'm going to then now share my screen. I'm going to stop sharing my screen, and I'm going to quickly go through some redox reactions and just give you some rules around redox reactions, okay? So all right, so if you just give me a few seconds and then I'll just load that up onto, okay. Right. Let me just quickly give you if I could just ask you, would you prefer me to go through equilibrium or acids and bases? Can I just have if you could just type out quickly, acids and bases or equilibrium, chemical equilibrium or acids and bases? You can just type out your responses, acids and bases, okay? Okay, 1, 1, 2, 1, 2, 2, okay. All right, okay, don't say anymore. I'll go through both. I'll do you a favor, I'll go through both, okay. Let's start with acids and bases, okay. Right, I'll go through both. Right. Okay. Right, let's look at acids and bases and let's see what we can do with them, how important they are, and why are they important, right? So, and whenever you see an acid, you know H appears in the formula, like HCl. See, HCl here is an acid, right? So it's a proton donor according to the Bronsted-Lowry theory. And whenever you see a base, it's either OH or a carbonate, right? And also NH3 is also a base, right? So you know, and everybody told you this, and you know this for a long time, acid plus a base will give you salt and water. So you know HCl plus NaOH gives you a neutral salt, NaCl plus water. Okay, so you know some properties about acids. They have a sour taste. How do you know it's an acid? It will turn blue litmus paper red. And what do you know about acids? They neutralize bases, right? So what about bases? They have a bitter taste. They have a very soapy feeling. So your soaps are basically basics, and they turn red litmus blue. So an acid turns blue litmus red, a base turns red litmus blue. Okay, and they neutralize acids. Right, now we have an Arrhenius acid, right? So an Arrhenius acid is a substance, when dissolved in water, increases the concentration of the hydronium ions. So whenever we see H3O plus, and you know what's H3O plus? It's H plus from the acid and water. So when H plus reacts, combines with water, we call this a hydronium ion, right? And this is, so an Arrhenius acid will donate, right? When dissolved with water, will give off H plus and form H3O plus. An Arrhenius base is a substance that increases the hydroxides, right? So what is a hydronium ion, right? So you can see, I told you, the hydrogen ion is a bare proton. So that proton comes from the acid. And when it donates the acid, like HCl, will give off the H+. As soon as it gives off the H+, this greedy water molecule is waiting, right? So it forms H3O+ because of hydrogen bonding. So most of the times, we represent the acid in water as the hydronium ion, right? And instead of writing H+, we just understand it as H3O+, as hydrated. You know some common acids: hydrochloric acid, sulfuric acid got 2 protons, it's a diprotic acid, nitric acid, acetic acid, vinegar, right? And polar covalent molecules in the pure anhydrous state, right? So you can see when dissolved in water, what has happened? HCl completely dissociates into H+ and Cl-. I'm calling it H+ because the H+ is coming from the acid, but because it's hydrated with water, it forms H3O+. That means there's no more HCl that's formed. That is how you know that HCl is a strong acid, when it completely breaks up into H+ and Cl- in water. Okay, so that's what we call a strong acid. Now you have a non-metal oxide and water. So for example, when you take SO3 and when you dissolve, when SO3 dissolves in water, it forms sulfuric acid. You've learned this in the contact process. S plus O2 gives you SO2, SO2 plus O2 gives you SO3, and SO3 plus H2O gives you sulfuric acid. So that's why we don't like to give off sulfur dioxide into the atmosphere, because sulfur dioxide, SO2, forms SO3, and the SO3 dissolves in water to form sulfuric acid. This reaction is a highly exothermic reaction, and you have learned this in the contact process. Okay, the last stage of the contact process. Now, what do you know about bases? These are basically ionic compounds that contain OH or O2 minus, right? So you can see again sodium hydroxide, right? If you take sodium hydroxide pellets and you add it to water, it will completely dissociate to give you Na plus and OH minus. So also we can form a base using a metal oxide like we did with a non-metal oxide. Now non-metals are coming from the right-hand side of the periodic table, or the S block elements, the P block elements. But if you got group 1 and group 2, so you can see if you take calcium oxide and react it with water, you get slate lime, right? Calcium hydroxide, remember, turns carbon dioxide turns lime water milky. So this calcium hydroxide is actually lime water. So when we take calcium oxide and dissolve it in water, you form calcium hydroxide. Then we have what we call molecular bases. And ammonia is a molecule. It's got one molecule of ammonia. And when you dissolve ammonia in water, you form NH4 plus and you give off the OH. So you see why we call it a base, because it pulls off the proton away from water and it forms the OH minus, but it gives it in very small quantities. Okay. Now, strong acids, weak acids, and bases, right? Strong acids or bases, as I told you, they completely ionize in water. So they're strong electrolytes. And there's the strong acids: HCl, H2SO4, HNO3, HBr, HI, HClO. So you can see all of them got an H. And as soon as they go into water, they give off the H, right? And they form H3O plus. So a strong acid completely dissociates, and basically it's a proton donor, right? Weak acids, acetic acid. This acetic acid doesn't like to give off this proton. So a weak acid or base is one that only partially ionizes in water. So acetic acid is a weak electrolyte. Strong bases will contain a high concentration of OH. So they're also strong electrolytes. And a weak base typically contains nitrogen, right? So we look at that. Right, so identify each of the following as an Arrhenius acid or base. Give the chemical equation for the reaction. Okay, but just as you know, you can see BaO if you react it with water, will form barium hydroxide. So that's basically an Arrhenius base, barium hydroxide. And here, H2S, when you add it to water, gives off H plus and HS minus. So it's a proton donor, and that is an Arrhenius acid. Okay, so here's the solution. The barium oxide reacted with water to form barium 2 plus and 2 OH. So it generated OH. And as I showed you here, the H2S give off 1 proton, and the H2O grabbed it to form hydronium ion and HS minus. So you can see you formed H3O plus, it's an acid. So whenever you generate H3O plus, it's an acid. Whenever you generate OH minus, it's a base. Okay. Then we have a much more easier definition, and it's the Bronsted-Lowry theory. So a Bronsted-Lowry acid is a proton donor. A Bronsted-Lowry base is a proton acceptor. You can learn off all of these definitions of acids and bases. Okay. Now, look here and look very, very carefully. Okay. Right. Now, if you have HCl and you react it with water, you form the acid H3O plus, right? And this becomes the base. So you've got your primary acid, and this becomes the base. Why? Because this particular H, according to the Bronsted-Lowry, gave off the proton. This accepted the proton. The H2O accepted the proton. So it's a base, right? And then this Cl minus can accept back the proton and form the HCl again. So it becomes a base. So you can see here's your acid, and there's the base that it formed. So we call that a conjugate acid base pair. And here, this is the base, and this is the acid it's formed. So that's a conjugate acid base pair, right? So as soon as you identify the compound that gives off a proton, it's acid. And when it forms the conjugate base, that means it can take on an acid to come back to its original form. Okay, so that's a conjugate acid base pair. So let's look at ammonia. In the same light, you can see now NH3 plus took a proton. So the water now is an acid because it donated a proton to the base. So this is a base, and here's its conjugate acid, right? Because it formed NH4 plus. And this was the acid, and it formed a base. So you can see the conjugate acid base pairs, right? So if you have an acid, it will have a conjugate base when it gives off a proton. If you have a base which accepted the acid, it becomes a conjugate acid. So there's the conjugate acid base pair here. Okay. So for conjugate acid base pairs, the stronger the acid, the weaker is its conjugate base. So HCl is a strong acid, but Cl minus is a weak base. Okay, as far as that is concerned. Now, formic acid is a stronger acid than acetic acid. Which of the following is the stronger base? CHO2 minus, so this is D, or the CH3COO, right? So here, you can see in terms of, you have to rate them as stronger acids and stronger bases, right? So formic acid, you can see you form the conjugate base. And for acetic acid, you form the conjugate base, right? So which of the following is a stronger base? So acetic acid is a weaker acid. So it will form a stronger base, right? Acetic acid is a weaker acid than formic acid. And you can get this from the Ka value. So remember, we said the weaker the acid, the stronger is its conjugate base. So acetic acid is a weaker acid than formic acid. Okay. Right, acid-base strength. So in any acid-base reaction, the equilibrium will favor the reaction that moves the proton to the stronger base. So you can see here, as I said, HCl plus H2O gives you H3O plus Cl minus. H2O is a stronger base than Cl minus. So that means the equilibrium lies far to the right. That means the H2O will take on the proton, right? Now, in the case of acetic acid, the acetic acid forms a stronger conjugate base. So therefore, it grabs the proton and pushes it back to the acetic acid, which is the reverse reaction. Okay. I'm sure you heard of amphoteric substances. Okay. Some substances can act as an acid or a base. So we refer to them as amphoteric, right? So water behaves as a base, a proton acceptor towards HCl, and as an acid towards NH3. So water can pull off this proton. That means it's acting as a base. And then water gives off the NH3 to form NH4 plus and forms a base. So water is basically acting as a acid and a base, right? So HSO4 minus and HCO3 are amphoteric. In Arrhenius definition, HCO3 can only act as an acid. Okay. So amphoteric means they can act as acids or bases, right? So HSO4 minus and HCO3 are amphoteric. They can act as an acid or they act as a base. So if you look at H2SO4, it can give off a proton or it can accept a proton and form H2SO4. That's why we're saying it's amphoteric. Okay. So classify the following as an Arrhenius acid or base or a Bronsted-Lowry acid as a base, right? So Bronsted-Lowry is basically a proton donor. So you can see HClO4 is going to donate a proton. And in terms of an Arrhenius acid, it's going to generate H3O plus in solution, right? So HClO is, so both in this case, HClO4 is an Arrhenius acid and a Bronsted-Lowry acid, okay? So HSO4 is an Arrhenius acid and a Bronsted-Lowry acid, right? And this is amphoteric because it can accept a proton and form the acid. So it can act as an acid or a base, okay? If you didn't do these examples, now this is in your theory and you'll have to learn your theory on that, right? So for the following reactions, label all the species as Bronsted-Lowry acids or bases, indicate the species that are conjugates of one another. So let's look at the first example, right? You can see the HPO4 2 minus now basically pulled off a proton from the NH4 plus. So NH4 plus donated a proton to HP, so you form H2PO4, right? So it's basically acting as a Bronsted-Lowry acid because it donated a proton to HPO4 2 minus, right? So then HPO4 becomes a Bronsted base, right? Because it accepted a proton from NH4 plus. If you look at the sulfate and water, water donates a proton, okay? Can you please mute your screen? Whoever's got their dog barking in the back, I know who you are. Can you please mute your screen because you're disturbing the rest of the students? Samsung SM-AF2F5, I know who you are. I can get you. Right, so in this reaction, you can see the H2O also donated a proton, so it's a Bronsted-Lowry acid, and the SO4 accepted a proton, which is a Bronsted-Lowry base, right? So if H2O, H2O donated a proton, then OH is its conjugate base. So H2O is an acid, OH is its conjugate base, right? SO4 accepted a proton, so it's a base, and HSO4 it's its conjugate acid. So you can identify conjugate acid-base pairs, right? Now, ionization of water, you know that H2O can ionize into H plus and OH minus, okay? So basically, you can write out an equilibrium constant and H plus OH gives you that, when we rewrite that out, the OH, your Kc is going to be H plus plus OH minus into Kc times H2O all squared. But your H2O all squared is a constant. Hence, we call the Kc Kw. So it's just deriving the Kw. So H plus and OH minus is equal to Kw, right? Because H2O is a constant. And Kw varies with temperature, right? So at 25 degrees, Kw is equal to 1,0008 times 10 to the minus 14, but usually we round it off to 1,00 times 10 to the minus 14. So the equilibrium constant for water is 1,00 times 10 to the minus 14. If the product of H plus and OH in this aqueous solution exceeds this value, the excess ions immediately combine to form water, right? So in pure water, we can calculate the H plus and OH minus because we know what's Kw, and it's going to be square root of 1 times 10 to the minus 14. So the concentration of H plus and OH in pure water is 10 to the minus 7 moles per dm cubed, right? So you should go, all of this is basically your theory, right? Now, pH and pOH and pKw. So pH is the minus log of the H plus or the H3O plus, right? And you can also get pOH, which is basically the minus log to the base 10 of the OH minus, okay? So we also have this derivation where pKw is equal to pH plus pOH, and it was derived from Kw is equal to H plus times the product of OH minus ions, right? This is theory that you would have known. Right, so in a neutral solution, the pH is equal to 7. In an acidic solution, the pH is less than 7. In an alkaline solution, the pH is greater than 7, right? So here's an example. Find the pH of a solution for which H plus is equal to 4,00 times 10 to the minus 5. So you simply take pH is equal to minus log. In your calculator, you will calculate log of 4,0 times 10 to the minus 5. You will see you get a negative value. So that's why we take the negative logarithm to the base 10 of that particular value. And your pH works out to be 4,398, right? So it's simply minus log of the H plus ion concentration or the hydronium ion concentration. Find, now if we gave you the pH, right, we want you to find the H plus. So in this example, you'll simply say pH is equal to minus log of H plus. That means minus log of H plus is equal to 5,643. And to calculate H plus, so minus log H plus is equal to minus 5, right? So you put a minus sign there. And H plus is 10 to the minus 5,643. So whenever you have the pH, to get the H plus, it's simply 10 to the minus of that pH value. And you can see it's 2,28 times 10 to the minus 6 molar, right? So it's quite easy to work out the pH values. Now pay attention to this here, acid dissociation. For a weak acid, you're going to dissociate to H3O plus and the conjugate base, right? So whenever you have a weak acid, the concentration of the weak acid is determined by the H3O plus. So if we take minus of the H3O plus, we get the pH of that value. So we can write a Ka. Now in this case, because water is a constant, we say HA is equal to H plus plus A minus. And that's how we can write out the acid dissociation constant Ka for the dissociation of the acid. So it's simply H plus, the product of H plus, times the product of the concentration of the conjugate base over the concentration of the weak acid. So here's your dissociation constant, right? The larger the value of Ka, the stronger is the acid. Okay. Sineo, can you please mute your mic? That student Sineo, I'm going to bounce you off the system. So the larger the value of Ka, the stronger is the acid. And obviously pKa is equal to minus log Ka, just like pH is equal to minus log of the H plus. Okay. And the base ionization is exactly the same. If you take a base, you add it to water, you get BH plus and OH minus. To write a Kb, it's going to be BH plus, the concentration of BH plus times the concentration of OH minus all over the weak base. And pKb is equal to minus log of Kb. The larger the value of Kb, the stronger is the base. So then we talk about neutralization of strong acids and strong bases. So here we're talking about HCl versus NaOH. If you start with 100 moles of a 1 molar or 1 mole per dm cubed HCl and add 1 mole of NaOH, right? So you basically get the equivalence point occurs when 100 moles of base has been added. So we simply want to neutralize the acid with a base or vice versa. Okay. So pH, I told you, if you take the acid HCl, it completely dissociates into H plus, which is equal to the HCl ion concentration. Then we'll say pH is equal to minus log of H plus and minus log of 1 molar, right? Basically, you can see we can calculate the pH. All right. Now I'm going to show you pH calculations for weak acids, right? pH calculations for weak acids. If you had formic acid and we gave you its Ka, right? So formic acid, you can see, is a stronger acid than acetic acid because it's got a higher Ka. So we're going to write the Ka for the dissociation of formic acid, right? So let's look at this example. Pay attention because this is going to come out in your exams. Calculating Ka from the pH. The pH of a 0.1 mole per dm solution of formic acid at 25 degrees is 2,38. Calculate the Ka. So if I go back to my definition here, can you see we wrote out Ka, right? So here, see, I wrote out Ka. It's going to be H plus and A minus over HA. If I've got the pH, I can calculate the H plus. But how am I going to calculate the other two? So let's go back to that example. And you're going to always get that example in your exams, right? So we're going to calculate the Ka. The pH of a 0.1 molar or 1.1 moles per dm cubed of formic acid, calculate the Ka of formic acid at this temperature. So here, there's formic acid. It dissociates to give us H plus and the formate and ion, its conjugate base. So there's the acid, there's the conjugate base. We got its H plus as 2.38. We can calculate the H plus, which is 10 to the minus 2.38. I showed you this before. And hence we got the concentration of the formate ion. Now, let's look at the formic acid. You started off with 0.1 molar. You started off with 0.1 molar. And when it dissociated, we know how much of H plus has formed. Remember, we calculated it from the pH. There's it here. So if I've got that, the same amount of the formate is going to form. And the change was, that's how much of the formic acid was given away. So at equilibrium, all you're going to say is you're going to write out Ka is going to be H plus the formate over the formic acid. So it's going to be 4,2 times 10 to the minus 3, 4,2 times 10 to the minus 3, all over 0.1 minus 4,2 times 10 to the minus 3. But you can see this is a very small figure. So if you just say that is equal to 0.1, it's fine because this is a very small value and it doesn't affect the 0.1. And as you can see, the Ka worked out to be 1,8 times 10 to the minus 4. So this is always going to come out in your calculations, okay? So again, if I gave you the pH, right? The pH of a formic acid solution at 25 degrees is 2,38. From the pH, I write out the dissociation, and I've got the pH at 2,38. That means the minus log of the H plus is 2,38. Log of H plus is going to be minus 2,38. H plus is simply 10 raised to the power minus 2,38. And that you put on your calculator and you'll get 4,2 times 10 to the minus 3 molar. Right? Now, I know that I've had 0,1 molar. I know that this has formed. I worked that out. The formate would has to be the same, because if I gave off from here H plus, then that amount of formate is going to be formed, an equal amount. At equilibrium, then I know this gave off that amount of the H plus. So therefore, it's going to be 0.1 minus the amount of H plus that was formed. So I write out the Ka. I know my H plus. I know my formate. That's 4,2 times 10 to the minus 3. 4,2 times 10 to the minus 3. And at equilibrium, it's going to be 0.1 minus 4,2. And I get the concentration of the Ka of that acid. Okay. So you can calculate the concentration of the acid from there. To work out the percentage ionization, you can see I take the amount of H plus here, right? And I put it at the amount of the initial acid times 100. You can see a very small amount of the acid ionized. Okay, so that's what we have in terms of the ionization. Okay, so here's another example. Calculate the pH of a 0.05 moles per dm cubed nitrous acid solution. Now, there's only two examples they can do. They can give you, right? They can, in the previous example, they gave you the pH, right? They gave you the pH in the previous example, right? The pH of a 0.1 molar was 2,38. Calculate the Ka. In this example here, they are saying to you, calculate the pH of a 0.5 moles per dm nitrous acid solution. So this is a weak acid. So you don't just take the minus log of that, only if it's a strong acid, right? So in this example, you have to know the Ka of that particular weak acid. And if you write out the ionization, HNO3 ionizes to give you H plus and on NO2 minus. So initially we've got that concentration. At equilibrium, we don't know how much is going to ionize, right? So we say that's going to be HNO minus X, H plus X formed and NO2 minus X. I'm sure you've seen a very familiar set out like this. If you set it out always set it out like this and you'll never have a problem. So the Ka will be given. So you got your Ka. Now that's X, and that's 0,5 minus X. You remember in the previous example, I told you that when I minused the ionization, it didn't affect this value here, right? So basically, we say X squared over 0.05 because this X is very small. So we make that equal to 0.5, okay? Assume X is small compared to 0.05. So we rewrite that as X squared over 0,05, which is equal to 4,5 times 10 to the minus 4. We solve for X, and your molarity of the H plus here works out to be 4,8 times 10 to the minus 3 molar, right? Then we simply take the minus log, right? The pH is minus log of 4,6 times 10 to the minus 3, and we basically get the pH of your solution, right? So acids and bases, and in terms of understanding how they ionize. Okay. So I'm going to stop there for now. At my next session, in terms of equilibrium, I want you to go through your equilibrium, and it'll be set out in exactly the same way as how I set this out. Initial concentration at equilibrium, and instead of Ka, you will write out Kc in terms of calculating your equilibrium concentrations. So like I did it for ionization of acids, your equilibrium this is basically showing you the calculation at equilibrium. Okay, so go through your questions, go through the examples, and you should have no problems in your calculations. Okay, so unfortunately, I have to stop there today. And thank you for your attention. All right. The session for tomorrow will be broadcasted. So if there's a session tomorrow, I will go over the equilibrium with you and the example, right? So I'm going to stop sharing my screen, and I will end this session at this point. Okay. Good luck. Please go through your examples and please study hard tonight. Okay. I'm sure you're going to do well in your exams.
Thank you, Dr. Bissessur. Okay, so we'll upload the videos and the other resources on the websites I posted earlier. And I've also posted email addresses so you guys can email specific questions for the tutors to go over. I'm just going to play a short video now on how you can apply to UKZN, and then I'm going to close the session off. Thank you for attending.
Part of the UKZN experience is the opportunity to be part of a community and to network with not only our world-renowned academics, but with future game changers and leaders. They do say that the extent of one's success can be attributed to those they rub shoulders with. Therefore, you must surround yourself with like-minded people. So, how do you become part of a community that is committed to your self-development? How do you become part of UKZN? First, you have to apply. All applications for undergraduate studies at UKZN are processed through the Central Applications Office, CAO. This is for both your course and student residence application. The application process is as follows. Step 1. Consult the CAO Handbook. This handbook provides a list of all qualifications available at UKZN. Step 2. Have a look through the various courses offered and choose a program that interests you and for which you meet the minimum requirements. As one of the top 5 universities in the country, UKZN promotes academic excellence. So meeting the minimum requirements does not guarantee you a place to study. Step 3. Find the program code linked to your chosen qualification. This is the code you need to enter in your application form. Okay, let me show you something. You see, a code has 3 parts. Example, for BCom in accounting, the code is KN-P-BCN or KN-W-BCN. Crazy code, right? Well, basically, the KN stands for UKZN, the middle part stands for the campus of your choice, P for Pietermaritzburg, W for Westville. Then BCN stands for the actual course. Make sure to get these codes right. Step 4. Use this program code when completing your CAO form, which is available from the CAO website. Your application will be sent to UKZN. You can always check the status of your application using your CAO number, ID number, or passport number on this website, www.caocheck.ukzn.ac.za. For more information, visit www.cao.ac.za. It's that easy. Pay close attention to closing dates for qualifications. For example, MBCHB closes on the 30th of June, whilst other undergraduate programs close on the 30th of September. What are you waiting for? Apply now and shape your future today.